In the previous trainings of the Danesh Kit channel, we learned about some power electronic components such as MOSFET, IGBT, and BJT. In this tutorial, we introduce amplifier circuits and their types. Amplifier is a general term used to describe signal amplification circuits. Since amplifier circuits are not the same, they are classified according to their circuit configuration and modes of operation. In electronics, small signal amplifiers are usually used in devices that have a weak input signal. For example, a signal from a sensor in the image display or a larger output signal, such as triggering relays, lamps, and speakers. There are many types of electronic circuits, from small signal operational amplifiers to large signal and power amplifiers, which are categorized under the amplifier group. The classification of amplifiers depends on things like signal size, physical configuration, and how the input signal is processed, the relationship between the input signal and the load current. You can see the types of amplifiers in the table. Amplifiers can be thought of as a simple box or block containing the amplifying device, such as a bipolar transistor, field effect transistor, or operational amplifier, which has two input terminals and two output terminals, ground being common, with the output signal being much greater than that of the input signal as it has been amplified. An ideal signal amplifier has three main characteristics: input resistance, Rin, output resistance, Rout, and the size of the amplifier, called gain, A. Regardless of the complexity of the amplifier circuit, their general model can be represented by this figure, which expresses the relationship between the three characteristics. The amount of amplification of the output compared to the input is called gain of the amplifier. Gain is basically the amount that the amplifier amplifies the input signal. For example, if the input signal is 1V and the output is 50V, the gain of the amplifier will be 50. In other words, the input signal will increase by a factor of 50, which is called gain increase. The gain of the amplifier can be obtained simply by dividing the output by the input. Since gain is a ratio, it has no units, but in electronics, the symbol A is used to indicate the amount of gain. Amplifier gain. As we said, the gain of the amplifier can be calculated by dividing the output by the input. This image shows the gain of the amplifier. Thus, there are three types of gain: voltage gain, AV, current gain, RE, and gain, AP. The power gain can be calculated by dividing the output power by the input power. Also, indices I, V, and P are used to indicate the type of amplifier. Amplifier gain or power is expressed in decibels or dB. Bell or B is a logarithmic, base 10 scale of measurement that has no units. Since the bell is a very large unit of measurement, it is converted to decibels with the prefix decibel, which is 1/10 of a bell. To calculate amplifier gain in decibels or dB, these expressions can be used. Since the voltage and current gain is 20 times the logarithm of the output to input ratio, the DC power gain of the amplifier is 10 times the normal logarithm of the output to input ratio. However, due to the logarithm, the power of 20 dB is not twice that of 10 dB. Also, a positive dB value indicates amplification and a negative value indicates attenuation. For example, an amplifier gain of plus 3 dB means that the output signal is twice the input signal, and minus 3 dB gain means that the signal is halved. In other words, the signal is attenuated. In an amplifier, the minus 3 dB point is called the half power point, which is minus 3 dB below the maximum point, assuming the maximum point is 0 dB. Example: calculate the voltage gain, current and power of the amplifier whose input signal current and voltage are 1 mA and 10 MV, respectively, and whose output current and voltage are 10 mA and 1 V. Also express these gains in decibels, dB. The various amplifier gains. An amplifier gains given in decibels, dB. In general, amplifiers can be divided into subgroups depending on voltage or power gain. The first is a small signal amplifier, such as preamplifiers, instrumentation amplifiers, etc. These amplifiers are designed to amplify input signals with very low voltage levels in the microvolt range for sensors or radio signals. Another type of large signal amplifiers are audio power amplifiers or switching power amplifiers. These amplifiers are used to amplify large input signals or to switch very high currents. Power amplifier. Voltage amplifiers are commonly called small signal amplifiers because they usually convert a small input voltage to a larger output voltage. Sometimes it is necessary to use an amplifier circuit to start a motor or to power a speaker. In these cases, a high switching current is usually required, which power amplifiers provide. As the name of power amplifiers, or large signal amplifiers, suggests, their function is to deliver power to the load. This power is more than the input power of the amplifier. Power amplifiers convert the DC power of the power supply into an AC voltage signal for delivery to the load. Although the gain of these amplifiers is high, their efficiency for conversion from source to output signal is usually low. A perfect or ideal amplifier would give us a 100% efficiency rating, or at least that in power would be equal to the out power. However, in reality this can never happen because some power is lost as heat and the amplifier itself consumes energy during the amplification process. Then the efficiency of an amplifier is given as follows. Ideal amplifier. We can define the characteristics of an ideal amplifier from the previous discussion in terms of gain, meaning voltage gain. The gain of the amplifier, A, must be constant for different values of the input signal. Gain should not be affected by frequency. All signals with different frequencies should be amplified by the same amount. The gain of the amplifier should not add noise to the output signal. It should also pre-remove all input noise. The gain should not be affected by temperature changes and it should have a good thermal stability. The gain of the amplifier must remain constant at all times. Electronic amplifier classes. Classifying amplifiers as power or voltage amplifiers is done by comparing the input and output signal characteristics. This is done by measuring the input signal when there is an output current in the circuit. As we know, in order for the common emitter transistor to work in the active region, base biasing is necessary. Adding a small base bias voltage to the input signal causes the transistor to produce the full input waveform of the output. Of course, by changing the state of the base bias voltage, the amplifier can operate in amplification mode in addition to full wave generation. According to the base bias voltage, there are different modes and working ranges that can be categorized. Working mode is better known as class of the amplifier. Audio power amplifiers are classified alphabetically into Class A, Class B, Class C, Class AB, etc., based on circuit configuration and operating mode. These classes range from low-efficiency near-linear output to high-efficiency non-linear output. None of the boosters is better or worse than the other and has a specific use depending on the need. Each of the different classes of amplifiers has a certain maximum efficiency. The most common class of electronic amplifiers. Class A amplifier, its efficiency is less than 40%, but its reproducing and linearity are suitable. Class B amplifier, its efficiency is about twice that of a Class A amplifier and, theoretically, about 70% at most, because it conducts for only half the input signal and therefore consumes power. Class AB amplifier, its efficiency is between that of Class A and Class B amplifiers, but produces a weaker signal than Class A amplifiers. Class C amplifier, this is the most efficient class of amplifier, but the distortion is high and only a small portion of the input signal is amplified, so the output bears little resemblance to the input signal. Class C amplifiers have the lowest reproduction. Introduction to the class of amplifiers. Class A amplifier. A Class A amplifier reproduces the input signal perfectly at the output. In this amplifier, the transistor is fully biased in the active region and therefore does not operate in the cutoff or saturation regions. As a result, the AC input signal will be exactly between the upper and lower bounds of the amplifier signal. In this configuration, the same transistors are used for both halves of the output waveform, and depending on how it is biased, the output current of the transistor is maintained even in the absence of an input signal. In other words, the output transistors never turn off. This is why Class A operation is very inefficient and the power converted from DC source to AC signal is very low. Usually, the output transistor of a Class A amplifier gets very hot even when there is no input signal, so a heatsink must be used. When the output current is not established, the direct current of the transistor, IC, will be equal to the load current. A Class A amplifier converts most of the DC power to heat, so it is very inefficient. Class B amplifier. Unlike a Class A amplifier, a Class B amplifier uses two complementary transistors, one NPN and one PNP, or one NMOS and one PMOS, to produce each output half wave. One transistor conducts half of the waveform and the other conducts the remaining half to the output. That is, half of the working time of each transistor is in the active area and the other half is in the off area. For this reason, it amplifies 50% of the input signal. In this class, there is no bias voltage, but instead, the transistor operates only when the input signal is greater than the base emitter voltage, about 0.7 V for semiconductors. Therefore, when the input is 0, the output will also be 0. Half of the input waveform appearing at the output makes the amplifier more efficient. In Class B amplifiers, the DC voltage is not used to bias the transistors, so a base emitter voltage, B, greater than 0.7 V is required to drive each positive and negative half wave in the transistor. Therefore, the lower part of the output waveform, which is below the 0.7 V window, is not generated. Because of this, there will be a distortion region where when one transistor turns off, it takes some time for the next transistor to turn on. As a result, a small part of the output waveform is at 0 voltage, which is distorted. This distortion is called crossover distortion. Class AB amplifier. A Class AB amplifier configuration is somewhere between a Class A and B configuration. Although in this class, two complementary transistors are used at the output, when there is no input signal, a very small bias voltage is applied to the base of the transistor to bring the transistor close to the cutoff region. The input signal causes the transistor to operate normally in the active region, thus avoiding any transient distortion that was present in Class B. This means that the transistor will be on for more than half of the waveform in one cycle. The gain and linearity of this amplifier class is higher than Class A. Class C amplifier. The Class C amplifier design has the greatest efficiency but the poorest linearity of the classes of amplifiers mentioned here. The previous classes A, B and AB are considered linear amplifiers, as the output signal's amplitude and phase are linearly related to the input signal's amplitude and phase. However, the Class C amplifier is heavily biased so that the output current is zero for more than half of a cycle of the input sinusoidal signal with the transistor off at its cutoff point. In other words, the conduction angle of the transistor is significantly less than 180 degrees and is generally in the region of 90 degrees. While this form of transistor biasing gives a much improved efficiency of around 80% to the amplifier, it introduces a very heavy distortion of the output signal. Therefore, Class C amplifiers are not suitable for use as audio amplifiers. Because of their extreme audio distortion, Class C amplifiers are commonly used in high-frequency sine wave oscillators and certain types of radio frequency amplifiers, where current pulses generated at the amplifier's output can be converted to perfect sine waves of a specific frequency. LC resonance circuits are also used in the collector circuit. The performance class of an amplifier is very important, and since the input signal must have amplitude, it is also necessary to bias the transistor. In the category of amplifiers, the input signal, efficiency and power consumption and power loss in the form of heat are considered. However, the types of amplifiers can be categorized in the table. Poorly designed amplifiers, especially Class A types, may require larger power transistors, more expensive heat sinks, cooling fans, or even increased power supply size required to provide the additional power dissipation required by the amplifier. Electricity converted to heat from transistors, resistors, or any other component will render any electronic circuit inefficient and lead to premature failure of the device. Now the question arises why we use Class A amplifier whose efficiency is less than 40% and not use Class B with efficiency more than 70%. This is due to the linear nature of the Class A amplifier in its larger frequency response. In this case, the Class A amplifier may consume even more DC power. In this introduction to amplifier training, we saw that there are different types of amplifier circuit, each of which has its own advantages and disadvantages. In the next tutorial on amplifiers, we will discuss the most common type of transistor amplifier circuit, the common emitter amplifier. Most transistor amplifiers are common emitter or CE circuits due to their high voltage, current and power as well as their excellent input-output characteristics.